So suppose we have something on the right hand side that's not a perfect square. How are we going to handle that? So this would be a perfect example. That guy on the right hand side is not a perfect square. And at first you might try to see which numbers fit. Maybe you could try x equals 2, maybe. But you see 2 squared is equal to 4, so it's not, doesn't cut it. Maybe you could try 3, but 3 squared is equal to 9, so you've gone too far. And so it seems that one of the solutions here might be a number somewhere between 2 and 3, so that when you square it you get 7. But it's not exactly a whole number or an integer, or maybe even a rational number. In fact, by trial and error you might be able to say, well, maybe it should be about 2.6. But if you try 2.6, you will realize that you're kind of short of 7. And say, well, maybe I have to add more things. And eventually, by trial and error, you could try something like this: 6, 4, 5, 7, 5, 1, 3, 1, 1, 0, 6. And you might still be close to it, but not exactly. And so the actual truth is that this number may go on forever and ever and ever and ever with no repeating pattern. Famous name for these numbers is called irrationals. But they're too long to write. It's hard to write that number. I'm not quite done writing it. In fact, even if I wrote 1,000 digits, I would still not be done, because there's infinitely many more to go. That's a huge number. Infinitely many numbers to go. That means that there's not enough ink in the world so that I could write them all up, because it's infinite, and the amount of ink in the world is finite. That's crazy. There are more numbers here than there are grains of sand in the ocean. Oh my goodness. Okay, so if this number is way too long to write, then we're not going to write it. So what do we do then? Instead of writing this number, we make up a new symbol. We create a new symbol for those numbers that are too long to write. Okay, that's how we handle that. And so we create a symbol called square root, or the radical 7. The radical 7 was born, was invented to represent a number such that when you take that number and you square it, guess what you get? You get exactly 7. That's it. What is that number equal to? It's about 2.6. But I won't tell you what the whole number is because it's just too long. Instead, we say the number that when you square it you get 7. But that's too long, so we just say radical 7. So that's a working definition of a radical. And we'll have more on that in just a second. Okay? So that's how these radicals were invented. And so one way to make it formal is like this: the definition of a square root, or sometimes called a radical. If it's a positive number, and that's kind of important for now, we'll have the definition when it's -1 later. If it's a positive number, the square root of a is a number that when you square it you get a. Okay? So for example, what would be the square root of 25? Well, that would be 5, because since 5 squared is equal to 25. There's more nuances here. The fact that there's only one, the positive solution, it takes a little bit more explaining, but this may not be the right place or time for it. Here, try another one. The square root of 36, well, that would be 6, since 6 squared is equal to 36. What about 81? Well, that would be 9. Why? Since 9 squared is equal to 81. What about the square root of 1/9? Well, that would be 1/3. Since 1/3 squared would be 1/3 times 1/3, it would be 1/9. And so on and so forth. Again, the square root of 13, when they're not even like that, well, there's not much you can do. You just all you know is that the square root of 13 squared is equal to 13, since that's equal to true by definition of radicals. That's a justification. Okay, that's a little introduction to square roots, and the reason we're doing all this is so we can complete the story about solving equations when the right hand side is not an even square. Alright, let's talk is cheap. I think we should get back to solving equations. Okay, let's get back to solving equations. So we return to solving equations, and we pay particular attention now to the ones where the right hand side is not an even square. Here we proceed as follows. I'm going to go with this type. Suppose this is given. I could say this is x squared minus 19 or minus 17 is equal to 17 plus negative 17. Cancellation law of addition, adding a negative 17 to both sides. That would give you that x squared plus negative 17 is equal to 0 by inspection. And here we go with something clever. I could write this as x squared minus 17 is equal to 0 by definition of a minus b. But here we go with something clever. This doesn't look like a perfect square. Well, it wasn't a perfect square 5 minutes ago. But now with the invention of the radicals, I could see it as a perfect square using the following idea. The square root of 17 is a number that by definition when you square it you get 17. So if I square this I do get 17. That's the definition of radical, and now everything has changed. Now I have this square minus a square, the difference of squares, and I proceed the same way I did earlier. X minus the square root of 17, x plus the square root of 17 is equal to 0 by difference of squares. And then I have x minus the square root of 17 is equal to 0, or x plus the square root of 17 is equal to 0. And that would be by zero factor theorem, because something times something is equal to 0, zero factor theorem time. And that gives you that x equals plus or minus the square root of 17 after you're done. And there you go. So this proves that the exact same steps still work. The same package still works even if the right hand side is not a perfect square. And so this is still SRP, again, square root property, showing off that it works no matter what the right hand side is, specifically if it's not a perfect square. Okay, so we formalize this into a package here. It's called the square root property. If x squared is equal to a, this is the perfect medicine to get rid of that square. To get rid of that square, you just get rid of it and have plus or minus the square root on the right hand side. Okay, that's the perfect medicine for it, the square root property. Alright, let's practice it some more, and then we'll be good to go. Oh, we should also have a little discussion about these square roots. Sometimes a little simplification is required. So for the rest of this lecture today, what we want to do is just practice the square root property a little bit, and then talk a little bit about simplifying these radicals. Okay, come back and we'll get that job done. So let's practice our newfound tool here, the square root property, to solve equations that look like this, that fit this pattern. Here we go. So if this is given, I'm going to go with x equals plus or minus the square root of 101. And that's by square root property. Bim. Done. Bam. Yippee-ki-yay. Super easy. That's the perfect medicine to get rid of it, that square root property. That was too easy. Let's try another one. Here the key things that I notice is that I've got an x squared on the left hand side and I don't have any x's on the right hand side. So to me this is all the same, just one constant. All I see is just one blah here. So I proceed x equals plus or minus the square root of that blah. 5 pi plus 11.7. Square root property. Yippee-ki-yay. We're done. Easy, right? Another one. Again, all I see on the right hand side is no x's, just some blah. So x equals plus or minus square root of 11 over 5 by square root property. So easy. This one makes it a little bit more interesting because I don't have just x squared, I have a 5 in there. So finally something interesting here. We slap a 1/5, that would be the perfect medicine to get rid of that guy. A 1 over 5 times 7 over 3. Cancellation law multiplication says I can slap anything on both sides, any real number. 1/5 will do the job to get rid of that, leaving me with x squared is equal to 7 over 15. And now I can use the square root property. X equals plus or minus the square root of 7 over 15 by SRP. Okay? Pretty easy, right? Alright, that's enough practice for square root property. The final thing for today, I think we should talk about a couple things about working with radicals. Sometimes you may want to simplify them, or sometimes it may be useful. So we should have a little tiny discussion here about these radicals. Come back and we'll do that.